So we're going to revisit calorimetry and specific heat for a little bit. And I want you to remember that the heat generated in chemical reactions can be measured by a technique called calorimetry. This is when you have your bomb calorimeter that we talked about. So you have your container is filled with water, and then you have your bomb container here, and you have your sample right in the center, and all of this is enclosed. It has a lid. You have a tool in here that is spinning the water constantly, and you have a temperature probe right in here to measure the temperature and tell you what it is. And you have an ignition source out here. Ignition source. And it will actually ignite your sample, and you can determine how much energy that sample is releasing based on the change in temperature of the water, and by performing the calorimetry problem using this formula here. Now, the heat lost or gained is what we would use. If we are taking the temperature of water, you need to do the mass of water. Even if you put in 15 grams of Cheetos or whatever, you need to know how much water it is, because you don't have the specific heat of the Cheeto. You use the specific heat of the water. Now you could say per gram of the Cheeto, you could do that, but you can't you're not measuring the change in temperature of the Cheeto itself. You're not using the specific heat of the Cheeto itself. So that is why it's not exact for the Cheeto. You can still measure it, because all that energy that Cheeto released, or whatever it is that you're burning, gets released into the water, and the water absorbs that energy change. So it is pretty accurate, even if you're not using the specific heat and mass of that substance. Now, Q is the heat gained or lost during the reaction, M is the mass, C is the specific heat, and delta T is the final temperature minus the initial temperature. Now, it's important to remember, this is the extra step. It's important to remember that whenever you're doing bomb calorimetry like this, that the heat gained by the water is actually the heat lost by the reaction. So the reaction's heat is actually negative the water's heat. We're going to do a practice problem. So we have the burning of 16 or 1.6 grams of methane and oxygen. So we've got that combustion, and we produce carbon dioxide gas and liquid water. It's in this bomb calorimeter. So inside, so that's filled with water, and that is filled with 1.52 kilograms of H2O. Inside, we have the 1.6 grams of methane. And then we take the temperature, and the initial temperature is 20 degrees Celsius. And it changes to 34 degrees Celsius. And it says, what's the heat of reaction for this combustion? So we're looking for the heat of the reaction. Well, we can't, given this information, we can't directly calculate the heat of the reaction, but we can calculate the heat of the water. And once we know the heat of the water, we can find the heat of the reaction because the heat of the reaction is equal to the negative heat that the water absorbs. So we can do this. It's just an extra step. So we have the burning of methane and oxygen causes the surrounding 1.52 grams of water. So that's our mass of water. Our mass of H2O is equal to 1.52 kilograms. Now, what we're missing is a specific heat. We don't have the specific heat for methane. We're burning the methane and we're not measuring the temperature change of the methane. But we know from earlier that the specific heat of water is 4.184 joules per gram degree Celsius. Now, I want to make sure that all my units are the same. I have joules, grams, and degrees Celsius. I have degrees Celsius for my temperatures. My mass, I have kilograms though. I can't leave that in kilograms because they won't cancel out. So I've got to change, just like we did in week 1, I believe it was. I've got to change my kilograms to grams. Now I know that there are 1,000 grams for every 1 kilogram. So I'm going to use that conversion factor here. I want grams, so the grams go on top. I want to get rid of kilograms, so kilograms go on bottom. I know there are 1,000 grams for every kilogram, so my kilograms cancel, and I get 1,520 grams of water. Okay, now I could plug everything into my equation. The Q equals MC delta T. So the Q of water equals my mass, which is 1,520 grams of water, times my specific heat, which is 4.184 joules per gram degrees Celsius, times my change in temperature, my T2 minus T1. So that's my 34 degrees Celsius minus 20 degrees Celsius. So I'm going to simplify before I plug it all in. And I have my QH2O, my heat of water, equals 1520 grams times 4.184 joules per gram degrees Celsius times 14 grams degrees Celsius. My Celsius will cancel out because I have 1 on top, 1 on bottom. Grams cancel out because I have 1 on top and 1 on bottom. So if I plug all of this in, I get 1520 times 4.184 times 14, 89,036 joules. because that's my 1 unit that's left. But I didn't want my QH2O. I wanted my heat of reaction. So if you look up here, we know that the heat of reaction is equal to the negative heat of reaction of water. So my reaction energy is negative 89,036 joules. I could take this and say how many joules per gram. And if I did that, I'd divide 89,000 if I wanted to know joules per gram. I would take my negative 89,036 joules over my mass of methane, which is 1.60 grams. And that would give me joules, the amount of energy per gram of methane. So this is how they determine calories per gram. Or they say a serving is this much size. This is how they determine calories per serving. They take what they consider a serving, however many grams that is, and then they take the amount of energy that was released and divide it by the number of grams. So if I wanted to know how much energy per gram, I would just say 89,036 divided by 1.6, and this would give me negative 55,648 joules per gram of methane, CH4. So that you could find the amount of energy per gram, if that is what you wanted to find. The question didn't ask for it, but you can take it one step further and find that if you so desire. So here, if all my writing, some people like to see everything written out and the thought process, and then others find that too distracting and they like seeing it written this way digitally. So whichever way works for you, it's fine. This is just a review of what I did on the previous slide. Here, though, I changed it to kilojoules instead of leaving it at joules because that's an awfully big number. Either one is fine, but if you're going to change joules to kilojoules, it's the same process as we did with grams and kilograms. You put what you want on top, what you want to get rid of on the bottom. The joules cancel out. And then, of course, we know that the Q reaction equals the negative Q of the water. So the heat of the reaction is negative 89,000 kilojoules, which makes sense because it released that energy and the water absorbed it. Now, a calorie is the heat required to raise the temperature of 1 gram of liquid water by 1 degree Celsius. A kilocalorie is what we use for food energy. It's a unit that's equal to 1,000 calories. So whenever you think of calories, we actually use the kilocalorie, which is a capital C. Whenever you use 1 degree Celsius, or 1 calorie per gram degree Celsius, that is a lowercase calorie. So whenever you want to calculate the number of calories in food, keep in mind that you have to find the kilocalories. And that's why calories is capitalized. It indicates the unit for food energy. So we know that 1 calorie per gram degree Celsius equals 4.184 joules per gram degree Celsius. Water is kind of the standard. So if you're finding the heat of reaction in terms of water, you're going to be using 4.184 joules per gram degree Celsius, or if you're looking for calories, it's calories per gram degree Celsius. We know that chemical compounds in food provide us with energy. Our body breaks those bonds and we absorb that energy. So that energy is released whenever our body breaks it down. We absorb that energy, and that's the energy that gets us, that we use to move about and do the things that we need on a daily basis. Fats provide about 9 calories per gram if you were curious. Fruits and vegetables provide less calories per gram. Okay, say we're going to measure food calories. We have a 1.00 gram sample of nuts. Nuts have a lot of healthy fats in them. And they react with excess oxygen in a calorimeter. The calorimeter contains 1.00 kilograms of water. So let's look at this. We have our calorimeter. It has mass of water equals 1.00 kilograms. And it has, so water has initial temperature, so Ti of the water, the initial temperature, is 15.40 degrees Celsius. The final temperature equals 20.20 or 20.20 degrees Celsius. We want to find the energy content of the nuts. We want to find it in kilojoules and calories both. So this is a little more involved. You've got to do 2 math problems. We know that specific heat of water is 4.184 joules per gram degree Celsius. And we know that the specific heat of water is 1 calorie per gram degree Celsius. We know that the change in temperature, delta T, is equal to 20.20 minus 15, that's degrees Celsius, minus 15.40 degrees Celsius. So that's going to be, let's put that in my calculator. 20.2 minus 15.4 gives me 4.8, a change of temperature of 4.8 degrees Celsius. Now, I noticed as I was writing down my specific heats that I have this in grams there, which means I need to change my kilograms into grams. Remember, we have 1 kilogram equals 1,000 grams. So if I want grams, grams go on top, kilograms go on bottom. It's 1,000 grams for 1 gram. My grams cancel out. So I have 1,000 grams of H2O. Now I can pop everything in. Remember, I have 2 different math problems. I have, if I'm first doing my heat of water in joules, I have my mass of 1,000 grams of H2O times my specific heat, which is 4.184 joules per gram degree Celsius, times 4.8 degrees Celsius. And this gives me 1,000 times 4.184 times 4.8. This gives me 20,083 joules. But it says express your answer in kilojoules per gram and calories per gram. We want the energy content of the nut. This is the energy content of the water. Remember, QH2O, negative QH2O equals the heat of the reaction. So the Q of the reaction is going to be negative 20,083 joules. We have to change it into kilojoules. There's 1 kilojoule for every 1,000 joules. Joules cancel out, so it's 20,083 times 1 kilojoule over 1,000 grams. So the heat of the reaction for the nut is negative 20.083 kilojoules. But we wanted to know kilojoules per gram. So we take the amount of kilojoules and we divide it by the number of grams, which is 1.00 grams. So this is just negative 20 kilojoules per gram. That's how much energy is in 1 gram of nuts. Now, we did that in kilojoules, but we also need to do it in calories. So we're going to take this and erase this part, and the rest we can keep because it's still the same information. We're just doing a different problem. So let's change it. And we're going to say the Q of the water. This time we're using calories. And it's got to be kilocalories. So Q of the water is equal to the mass of the water, which is 1,000 grams, times 1 calorie per gram degrees Celsius, times 4.8 degrees Celsius. Degrees Celsius cancel out, grams cancel out, and we have 1,000 times 1 times 4.8. That gives us 4,800 calories. Now, we're not done because we need to find the Q of the reaction. Remember, the Q of the reaction equals the negative Q of water. So Q of the reaction then equals negative 4,800 calories that we have to change into kilocalories. 1 calorie, or 1 kilocalorie, I should say. So 1 calorie, that should be, that's a capital C, equals 1,000 little calories. So I set it up just like I did before. I want 1 calorie and 1,000 little calories. Calories cancel. So the Q of the reaction then for the nuts equals negative 4.8 kilocalories. Now we have to do per gram of sample. So we divide it by 1.00 gram. So the answer then would be negative 4.8 calories per gram. I know it's a lot of math. We just did 2 math problems for this one. Now let's talk about some energy economics. Aluminum is produced by the electrolysis of bauxite, and that takes a large amount of energy. Now, there are about 15 to 20 cans that can be made from recycled aluminum with the same energy it takes to make just one aluminum can from scratch. So it saves a lot of money, energy, and fossil fuels when we're actually recycling. I have a sister in New York City, and every household has to recycle. If you do not, you're fined. I don't know how they determine which house isn't doing it, but they have their ways and they'll find. They also require you to compost, which I found very interesting. Now, most energy used is in the form of electricity, and that's produced from fossil fuels, typically coal. And using catalysts will save energy because it reduces the activation energy. So we have a few questions I want you to try on your own and then come back and check your answers with us. So this first question here, a 2.00 gram piece of energy or piece of candy. So already I'm going to pull things out. We're given a mass of 2.00 grams. It's burned in a calorimeter containing 500 grams of water. So this is mass of candy. The water mass equals 500 grams. The water's temperature rises. So the initial temperature of the water rises from 22 degrees Celsius to 30 degrees Celsius. What's the energy content of the candy in kilojoules per gram? So we're looking for kilojoules per gram. To do that, we have to find our heat, which is Q equals mc delta T. We know that we're dealing with water, so our C is 4.184 joules per gram degrees Celsius. We choose that one instead of calories because it wants our answers in kilojoules. And now we can find our delta T. So our delta T equals our 30 degrees Celsius minus 22 degrees Celsius to give us 8 degrees Celsius. Now we can plug all of this into our Q equals mc delta T. So Q of water equals our mass of the water, which is 500 grams, times our specific heat of water, which is 4.184 joules per gram degrees Celsius, times our change in temperature, which is 8 degrees Celsius. So 500 times 4.184 times 8 gives us 16,736 joules. Now we need the Q of the reaction. So the heat of the reaction is going to be negative 16,736 joules. We need it in kilojoules per gram, though. So first, we have to change our kilojoules, our joules into kilojoules. So I know that there are 1,000 kilojoule or 1,000 joules for every kilojoule. I want kilojoules on top. My joules will go on the bottom. 1 kilojoule for every 1,000 joules. Joules cancel. And this gives me the heat of reaction is negative 16.736 joules. But I need it in joules per gram. So that means I need to take my answer and divide it by how many grams I have of that candy. And I have 2 grams. So if I take 16.736 and I divide it by 2, I get that each gram of candy has 8.37 joules per gram. I know it's a lot of math, but you can do it. Okay, just remember to take your time, write everything out, look at your units, make sure that they cancel out, and you're left with the correct units. You know that the heat of the reaction will have to have its answers in joules. So if you are canceling out correctly, you'll have the correct unit. Let's look at this next one. We have a 1.50 gram sample of a snack bar, and it raises the temperature of 1 kilogram of water from 18 degrees Celsius to 26 degrees Celsius. What's the energy content of the snack in kilojoules per gram? Same process as up above. We have our mass of water equals 1,000 kilogram or 1,000 grams because it's 1 kilogram and we know that 1 kilogram is 1,000 grams. So I just did that conversion in my head. We have the initial temperature, 18 degrees Celsius. Our final temperature is 26 degrees Celsius. We have our C of water equals 4.184 joules per gram degrees Celsius. And we have our mass of sample. Our sample mass is 1.50 grams. I'm going to go ahead and calculate the delta T. It's 26 degrees Celsius minus 18 degrees Celsius. This gives me 8 degrees Celsius again. Now I can plug everything into my equation. The cube of water equals my mass of water, which is 1,000 grams, times 4.184 joules per gram degrees Celsius, times 8 degrees Celsius. Degrees Celsius cancels, grams cancels. So my Q heat of water is 1,000 times 4.184 times 8 gives us 33,472 joules, but we want to change those joules into kilojoules. So I'm going to say times 1 kilojoule for every 1,000 joules. Joules cancel, and that gives me 33.472 kilojoules. Now, I'm not finished because I want to know in kilojoules per gram. And this is just the water. So I need to take my heat of reaction then is my negative water value, so negative 33.472 kilojoules, and I divide that by the amount of grams I have, which is 1.50 grams. Doing this math will give me my answer in kilojoules per gram. So I take the negative 33,472 and divide it by 1.5, and I get 22.3 kilojoules per gram. There you go. We're going to stop there, and we'll see you next time.